Thanks a lot. So thanks a lot to the organizers for the invitation and the opportunity to talk here. It's actually my first SciPy conference, so I'm excited, and I'm also lucky that I can actually present my work here in the following presentation. So I'm going to talk about Pylira, which is a Python package for deconvolution of images in the presence of Poisson noise. The presentation is going to be split in two, roughly. So in the first part, I'm going to talk about the actual statistical method, and in the second part, then I'll talk about the actual package and show some application examples. A first few words about myself. So I'm a postdoc at the Center for Astrophysics in Boston. I'm by trade a gamma ray and X-ray astronomer, but I'm also very interested in open source scientific software development in general. And I would also call myself maybe a self-taught statistician. I'm also a member of the CHASC Astrostatistics collaboration, which is like a loose group of statisticians and astronomers trying to collaborate on statistical methods and applying those to astronomical data. The benefit there is that astronomers learn about statistics and statisticians find actual applications for their algorithms and their methods. The group has a webpage that I've linked here, and it also has a dedicated GitHub organization that you can find there below. I'm also one of the lead developers of a package called GammaPy. I'm not going to talk about this today, but it's a Python package for analysis of astronomical gamma ray data and science tools library for the Cherenkov telescope array. I also link my GitHub profile, so if you want to follow me or contact me, then you can do this via GitHub. Okay, let me start with a quick introduction and talk about the low counts imaging process. So how does that work? Assume we have some imagery or some thing of interest that we want to observe. In this case, it's a selfie. We have a telescope or an instrument or a camera that we use to take the picture, and this has a finite angular resolution. And this is typically quantified by the so-called point spread function. Typically has some kind of Gaussian shape, but it can have arbitrary shapes like, I don't know, can have diffraction patterns or can be asymmetric, something like this. If after the application of the point spread function, then basically the data or the image that you are taking will be blurred. So this is what it looks like after this. Then in addition, especially for astronomical observatories, there's the definition of an exposure, which is a combination of the detection probability within the image for a given photon, and this multiplied with the observation time. So you can have, for example, multiple pointings of a telescope in multiple or different positions of the image, and this way you will have different exposure in the image, and this could look like this example, and after the data looks like this. Then finally the low count step. So in this case we are typically dealing with very, very low intensities and very low fluxes. So it's very, very bad signal to noise ratio, and we're basically just detecting individual photons of the source of interest. And this means all the data that we are dealing with is subject to Poisson count statistics. And this way you introduce some noise, and this is what the data then looks like after. So what is now the problem of the unblind deconvolution? So we have the data on the left, which is the counts. So these are the things that we can actually measure. And the question is whether we can actually improve the quality, reduce the noise, and improve the angular resolution of the image again, such that we end up again with this selfie or a nicer image here. Typically, of course, I mean, especially for astronomical images, we don't have any ground truth, or we don't have anything to compare to. And in this case, I mean, also selfies and X-rays or gamma rays are probably not recommended anyway. So let's just change to an astronomical example here. So this is what real data could look like from an X-ray instrument. And then the question is whether we can reconstruct the data given some estimate of the point spread function of the instrument and the exposure. This is what is called unblind. So the point spread function of the instrument is either known or it can be simulated, and also an estimate for the exposure is actually known or can be simulated. And then we can use some fancy statistical method and retrieve, for example, a very nice deep sky image just from this Poisson. Of course not, but I couldn't resist and just use one of these nice web first deep field images. But the goal is, as I said, like to reconstruct the image using statistical methods. This is typically called an ill-posed inference problem. Ill-posed means in this case, the solution doesn't necessarily have to be unique, and typically also is not necessarily continuous in the solution space. Let me quickly address like the big elephant in the room question. So we could just use machine learning or some deep learning. This is what like everybody does nowadays. But I want to motivate quickly why we're not doing this here in this case. So first of all, of course, I mean, there's a lack of training data. Typically, astronomical images from X-ray and gamma ray observatories are very expensive. The observation time is very limited. And you cannot just generate like an arbitrary amount of images. Then second, there's just no ground truth. We don't know what the sky really looks like. We only have the data that is observed and distorted through our instruments, so there's actually nothing really to compare to. And then also like standard deep convolutional network architectures are not necessarily suited for this deconvolution task. For example, I've put one reference, so they can, for example, learn like something like a pseudo-inverse PSF kernel, so you could actually apply this kernel in the spatial domain to sharpen the data. But this then requires like learning very large kernels and having very adapted architectures, making use of tricks like separability of the kernels. Here are a few other arguments. So for Poisson data, one is always in the low signal-to-noise regime, so specifying actually the type 1 errors, so something like a false detection or a false feature in the image is actually very important. And ideally, one can keep track with the method of the complete likelihood, and this is not given for all machine learning models. For some it is, but not for all. Then in addition, there also one needs to learn some information that is actually available a priori. This is typically like the Poisson statistics of the data. We know that the data will follow the statistics, so there's no need to learn it. We just know that this is the case. However, I think like maybe some transfer learning or simulated training data could maybe work, but this is something that I'm not exploring here. Okay, so instead we're relying on what I call like a classical statistical method. Or inference method. This requires just a little bit of math. So for the counts image, one assumes like a per pixel Poisson likelihood. This is what's given here, and then one can define like the total likelihood just by multiplying all likelihoods across all pixels. And then as usual, one just takes the negative log likelihood. In astronomy, one ends up with a statistics that is sometimes called cache statistics. And D in this case is just the data, so these are the counts that we've measured. And lambda in this case are the model counts, so these are the counts that we're trying to predict. And in this case, it just consists of this image X. This is the one that we're trying to reconstruct, and a model of the PSF, and this X is then just convolved with the PSF. One could, in general, consider like each of these pixels xi as an independent parameter in the model. But then just straightforwardly, one could solve something like this, for example, using a classical gradient descent approach. So we just take the derivative of the likelihood or the cache statistics here with respect to all parameters. Then you scale it with some step size or learning rate. And then given some starting estimate for your image, then you can actually run an iterative algorithm that improves then your estimate until you converge, ideally maybe to a maximum likelihood estimate. And an alternative solution for this was actually already proposed like 50 years ago. This uses, instead of gradient descent, something called expectation maximization, and this was introduced by Richardson and Lucy at the same time. And this is what the update rule then looks like for this case. This is one of the standard methods to deconvolve data, but it has some flaws. This is what I'm trying to show here. So if I just apply this standard Richardson-Lucy method, this one, for example, is implemented in scikit image in the restoration sub-package. If I just apply it to this data, then you can see that with one iteration, it already improves the sharpness. With 10 iterations, It also improves, but then at some point it starts to decompose the data into these many point sources, and you get like you get a reconstructed image that is not really close to your ground truth anymore. The reason for this is now if you take a look at the reconstruction convolved with the PSF again, you fairly get actually like a good prediction of your model counts, even after the PSF convolution and even after this 1,000 iterations here. And the same is confirmed, for example, if you just take a look at the residual count. So this is the predicted, or this is the measured counts minus the predicted counts from the reconstruction. So these are like fairly good residuals. But indeed, like all of these reconstructions show good residuals and good model counts. But the reconstructions that we actually have are actually very different, and there's no way around this. I mean, this is just the definition of the ill-posed problem. So there are some possible solutions. One is what I would call like pragmatic. This is what people have been using in literature a lot. So just early stopping of the Richardson-Lucy algorithm. So limit the number of iterations until one, let's say, like visually likes the result. This is often used and typically also good enough for showing nice images. So this is something that has been done. Then there are variations. That I would call like an engineered solution. This consists of adding additional regularization terms to the likelihood function. Some of the better known ones are total variation or the Tikhonov regularization. And those often require introducing additional like hand-tuned parameters. And then third, there's solutions that I would call maybe like statistically closed, and those would include then prior information or assumptions on the likelihood, and one basically changes to a fully Bayesian treatment of the problem. And this is actually the method and the application, the algorithm that is actually implemented in LIRA. So this is the LIRA method. Starting from the same log likelihood function that we had before, now we're just adding a log prior term that only depends on lambda. So the goal here is to restrict the solution space for lambda or for x using prior information. So the LIRA method here has like this very specific special multiscale prior to achieve smoothness of the image and the solution on multiple scales. And the initial idea implementation is already from 2004. I'll explain this a little bit more in detail after this slide. And then there was also another slight modification in this LIRA method then proposed in 2011, where the model counts can now actually be extended by the exposure, so one can take the exposure into account, and also optionally a baseline or background component to the model. And then, as it's very common, with the Bayesian treatment of the problem, one also just changes from expectation maximization to an MC-MC sampling from the log posterior function here, and effectively one starts sampling a series of images that are compatible with the log posterior. Just a few more details on this multiscale decomposition. So this is the effective prior that is implemented in this method. So starting from an image like this, one defines a quadrant consisting of 4 pixels, x1, x2, x3, and x4. And then those are summed. And this way you obtain like a next level of the multiscale representation. So all the counts contained in these 4 pixels are now contained in a single one, and the size of the image is reduced by a factor of 4. And then, in addition, one creates this larger image by just dividing again by the total number of counts, and now each pixel actually contains like the fraction or the split proportion of the total sum of these four pixels here. And this way, each of these values of x hat here is between 0, 0, and 1. And then one can continue like this on the next level of the multiscale representation and the next level like so, until one basically ends up with a single pixel that contains like the total number of counts in this image here. This multiscale representation is then the basis for the actual prior that is introduced, and one suitable choice here was this so-called Dirichlet distribution. It is a multivariate distribution where all actually variables sum to unity. And the larger this alpha k parameter here gets, the more similar those variable values are. And this effectively is a method then to smooth the image on multiple scales. So if you choose a larger alpha k value, then those x hat values will be more similar, and you have a way of smoothing and controlling the smoothness of the image. In addition, in this method, there is an additional hyperprior on this alpha k parameter, which just was proposed with an empirical form, the one that I'm showing here. And you can see that it peaks, for example, at around 1 or around 2. And this effectively, you can imagine this alpha k parameter as of like adding hallucinated counts to the image, and thus like smoothing the image. Okay, this is the LIRA method. This was actually implemented originally as an R package in 2011. The original code is still available. But meanwhile, Python has become basically the favorite language of choice for astronomical data analysis, and I decided to, let's say, like revive this Python package and write this R package and write a Python wrapper for it. So Pylira is effectively a Python wrapper around the initial C or R implementation. This is implemented via PyBind 11. I think on Friday there's going to be in the maintainers track another tutorial on PyBind 11. This is highly recommended. So PyBind 11 works very, very nicely. And then I also decided to put this into a package, AstroPy affiliated package template. In addition, there are dependencies like NumPy, SciPy, AstroPy, Matplotlib, so standard dependencies from the scientific Python ecosystem. The code can be found on GitHub, so astrostat/Pylira, and also there's documentation that you can find on Read the Docs. Here's now a short code example from Pylira. This is fully working, and basically all that you need to do, you start with the usual imports. Then there's a main API that is called the LIRA deconvolver class, and then there's some test data built in that you can import from pylira.data. This is typically used for testing. Or tutorials and illustration. In this case, it's just a very simple test case, so it's like a point source and a Gaussian PSF. Then I'm initializing the random state here with NumPy. Then I'm loading the built-in test data sets. Data here, this data variable is just a normal Python dictionary, which contains then like well-defined keys like counts, PSF, optionally exposure and background. Then we have to define an initial estimate for the flux. This is just done here with a random instantiation, so it's a random image. And then one can configure this LIRA deconvolver class. The API here is very much inspired from scikit-learn. So the idea was to take all configuration of the class on input and then actually pass the data to a run method that then actually executes the algorithm. So here are these alpha k values that we can specify for the initial values. Then you can specify the maximum number of iterations on maximum number of samples that you want to draw, and then you can define a burn-in phase for the MC-MC chain to actually converge. Then you can run the algorithm, then the result is going to be stored in result object, and then you can just write the result, for example, to a FITS file. This is a file format, of course, that is very common for astronomy. Then Pylira implements a few little convenience methods like diagnostic plots. So here's one thing that you can do. So based on this LIRA deconvolver result, you can plot, for example, the trace of an individual pixel in the sampling process. This is what is shown here. So it shows the trace of the center pixel, and also shows in blue, and it also shows the surrounding pixels in gray. And this way you can see, for example, whether there are correlations between neighboring pixels. Or specifically in this case, for example, the burn-in phase was chosen to be, I think, 100 samples. But you can see that up to this point, the MC-MC chain has not converged. And in this case, it would be more wise to choose like a different burn-in phase. But this is what these diagnostic plots are useful for. There's another one. So this just shows the trace of these alpha k smoothing parameters. And this, again, is like a very good diagnostic tool for checking whether the algorithm has actually converged in the region of your interest. The goal here for me was really to provide as much as possible additional diagnostic information, because I think it's really important to check and whether you can trust the sampling results, and key to this is typically the visualization of results and checking for plausibility. Okay, let me show you one real application example on real data. Maybe you've heard about, I think by now everyone has heard about the James Webb Telescope, but maybe you've heard about the CHANDRA Observatory as well. So CHANDRA is a space-based X-ray observatory which has been in operation since 1999. It consists of an imaging optical system for X-rays, and it has multiple instruments for different scientific purposes, like a high-resolution camera and an advanced imaging spectrometer. The typical angular resolution of CHANDRA is 0.5 arcsecond. This is already not that bad. And then it covers an energy range of 0.1 to 10 keV. So here you can see an image taken with the CHANDRA Observatory of the Crab Nebula. So the remnant of a supernova explosion that was in 1054. But still, typically, once you're looking at lower fluxes, or once you start looking into details of image, then you're typically still limited by the angular resolution of the instrument. One example for this is the Galactic Center region. So this is like real CHANDRA data from the Galactic Center. In the upper left, you can see the size of the PSF. In the center, you can see, or the actual counts data are shown on the left. And then in the center, you can see the reconstruction from the Pylira algorithm. And on the right, you can see reconstruction from the Richardson-Lucy standard method, in this case with 100 iterations. And you can see that the Pylira algorithm indeed leads to like a much smoother reconstruction of the data. Let me quickly visualize the sampling process. So this is the chain of images that are sampled by Pylira. So starting from 0, you can actually see that this point source, the bright point source, starts shrinking, and the angular resolution actually improves. And then, like, the bright features in the image are typically very stable, and there's no flickering in those pixels. And then background regions, like all these dark regions around there, you can see, like, typically are dominated by noise. And this is where you see all this flickering. In addition, I'm choosing just this one point source of interest here. And this means for actually each pixel, we get like a full distribution of the values in the pixel counts. And then you can even integrate those, for example, in a circular region that is of interest. And this is actually a very nice feature here, because in addition to the actual reconstruction of the image, you also get an error estimate, and then you would report the mean value as the reconstruction, and you can, for example, report the 1 sigma width here as an error of the reconstruction. Let me come to my summary and give a brief outlook. So Pylira is a Python package for deconvolution of images in the presence of Poisson noise. It acts as a wrapper around an original C or R implementation. I think the LIRA method is a nice example for what I would call like a pre-machine learning era method, which is like statistically fully traceable. So you can actually get like you can compute the full likelihood. And so it even delivers error estimates and even per pixel distributions, which is like very, very valuable information, especially in the low counts or low signal to noise regime. The current implementation is based on the initial C code. This is currently rather inflexible. For example, the choice of the prior that I've shown here, this is hard-coded and fixed. But there's a plan to extend the API to allow for more flexible prior definitions. I was also thinking maybe to re-implement the methodology maybe on a bit more modern technologies such as PyTorch or JAX to take advantage from GPU acceleration. And possibly it could be interesting to maybe combine this algorithm with machine learning based methods, for example, by actually learning the prior information. So thanks a lot. This was actually my last slide.
Okay, thanks for the excellent talk and also for basically being perfectly on time. So that's always nice. So we do have a few questions. Okay, so we have one from Matt. Is there anything that restricts the use of Pylira to gamma and X-ray astronomy, or could it be used with any situation in which the signal-to-noise ratio is low?
There's no restriction to astronomy. That's why I've tried to keep the API as generic as possible, so it just works with Python dictionaries and NumPy arrays. There is some functionality that is imported from SciPy, but this only concerns the fit serialization. This is pure convenience. If you have the possibility, for example, to get your data into a NumPy array, then you can use Pylira for this. I could imagine, I think there are situations, for example, I don't know, special kind of microscopy techniques that might end up with similar data.
And this is more of a development question for me, but so as Pylira uses PyBind 11, which is great, to create the Python API for the underlying C, is there future interest and plans in maybe adopting nanobind to pick up C++17 for perhaps further optimizations?
Yes, so something like, as I said, or I've given here in the outlook, I mean, we've seen the performance of the algorithm is okay. But the problem there is that it does not really scale to large images. And by large, I mean like millions of pixels. Typically, the examples that are shown here have like 10,000 of pixels. I was very happy with the PyBind solution for now, but still, like, if we plan to extend the algorithm, then we have to go back to the C code and, for example, implement a new prior. And at this point, I thought, okay, maybe it's really rather a feasible solution just to re-implement based on one of the more modern packages such as PyTorch and JAX that also do like the automatic differentiation and possibly using GPU acceleration. So I think at this point it's not 100% obvious whether the actual C implementation will be developed further or just kept for archival purposes.
Okay, and then just a comment is that everyone loves your animations, so those were fantastic. So let's thank our speaker again, and
thank you.